explanation has been something different, recommended as the hypothesis of the old interminable impact. Different assessments, other than those made by a huge number of inspectors, support this idea, giving affirmation about how the universe started. At any rate, the current universe of science, with new developments, brings us novel examinations and points of view. These evaluations challenge spots of view where certain pieces of data, for instance, those from Neil deGrasse Tyson, have transformed into a huge expansion in this affecting universe of science. Now, something drawing is happening with the James Webb Space Telescope. Seeing something as critical as this could make us question the hypothesis of the universe's start. The James Webb Space Telescope has seen 750 new universes. These structures are not exactly what we expected, driving us to reevaluate what we anticipated, as we had little consideration for them. This disclosure should help us appreciate how gigantic structures ended up being. So it's not surprising that it's stirring up how we would have the decision to relax the universe before. Experts said that the Big Bang Theory was an excellent explanation for how the universe started. By this theory, around 13.8 billion years ago, the universe showed up through a stupefying event, like the insane story of the main involvement on the planet. Anyway, the photos from the James Webb Space Telescope have challenged this thought. These photos show universes that are more subtle, smoother, and, in some cases, appear to be unlike anything predicted by the theory of how things became. According to the theory, as the universe grows, items should look more recognizable the farther away they are. However, these grand plans make an effort not to keep that standard. The hypothesis also expresses that at the universe's true beginning, all of the matter that makes up the universe was squeezed into a single superpoint called a singularity. This singularity was unbelievably more boiling than anything we could really quantify or measure. This idea of a singularity comes from a great arrangement of conditions in science proposed by Albert Einstein, considered general relativity. Inside the singularity, all the stuff in the universe was crushed into a small space with unbelievably high density. It was a beast proportion of mass and energy stuffed into a little space. In simpler terms, specialists have consistently said that the theory of how things came to be was the way the universe started. These new pictures from the James Webb Space Telescope are making us question that thought. The universes it found do not fit with what the hypothesis expected, and the theory's explanation of the early universe may not be as strong as we once thought. In our current perspective of the universe, we see that all the energy in the universe started from a very hot and thick point called a singularity. This point looks like the starting stage for all that we view as in the universe today. After this singularity, the universe began to expand and make over, by and large, 13.7 billion years, to become what it is today. The expansion started with something else, referred to as the Great Expansion, where the universe became unfathomably rapidly, basically faster than the speed of light. Maybe the very fabric of space itself was growing, and everything in it was stretching along with it. This huge expansion helped shape the universe by making things more uniform and making way for universes, stars, and other effects to form. As the universe continued to expand, it didn't grow as fast as during the momentous expansion. However, it still kept expanding. We call this predictable headway, astronomical progress. Specialists have seen proof of this increase through things like the way light from far-off universes changes in color, known as redshift. Now, let's look at those shocking pictures of new universes taken by the James Webb Space Telescope. To the general public, these photographs look dazzling, with assorted universes in a particular range. However, for inspectors, it's all the more surprising that these photos don't match what their theories expected. As a matter of some significance, these universes are basically shockingly prearranged, which challenges our perspective on structure, plan, and development. As shown by the speculation of the old Big Bang, there are more complicated designs than we expected. The hypothesis of the universe's start made assumptions about the number of designs there should be and how they should be spread out. However, the JWST pictures show a giant number of universes, some more than guessed. This makes specialists question whether the speculations checks are accurate. Several specialists are at any rate starting to overcompensate a little, pondering the way these revelations try not to fit into their ideas. Another shocking piece of the new grandiose plans is their impeccable smoothness, which clashes with what the theory of how things became proposed. As shown by the theory, universes should show peculiarities and plans in their shapes, based on how they formed and grew. Anyway, photos from the JWST show universes that are incredibly smooth, without the ordinary complexity and savagery seen during the early development of the universe. All that makes up our universe was consolidated into a tiny space. As the universe extended and cooled, changes occurred in particles like protons, neutrons, and electrons, which began to interact with light and energy around them. These interactions played a huge part in the development of matter in the universe. In the first few moments after the Big Bang, there was a process called nucleosynthesis, which involved the formation of lightweight parts like hydrogen and helium. These parts set up the development of stars, worlds, and other complex components. As persistent history unfolded, this mix of major building blocks was a critical stage in the universe's improvement, advancing from an initial condition of particles and energy to a state where matter began to form. As anticipated, the theory of the old Big Bang had expected to see universes that were scattered and chaotic. Anyway, the JWST pictures tell an alternate story. Instead of what the theory predicted, they show a different pattern of cosmic structures. Blustery, scattered universes. The photographs uncover smooth, round, and twisting shapes looking like the systems we find in the current-day universe. This upsetting disclosure challenges the conviction that disorder is an ordinary piece of universe improvement. On the off chance that there are not many or no fierce occasions happening in these universes, as proposed by the hypothesis of how things came to be, it becomes irrational that little universes would be fit for creating to turn out to be more critical. Also, the optical peculiarity predicted by the creating universe hypothesis, where objects appear smaller with increasing distance due to development, doesn't seem perceptible in space. Specialists have noticed a striking model where huge plans will frequently gather in monstrous gatherings, forming different relationships across the universe. This tremendous degree structure lines up with the suppositions made by the hypothesis of the universe's origin. As per the hypothesis, the universe started in a very hot and thick state and then expanded and cooled over time. As the universe extended, gravity assumed a huge part in shaping how matter was distributed and in organizing worlds. The gravitational impacts predicted by the hypothesis of the old Big Bang are consistent with what we see today, with gravity coordinating matter, causing the gathering of immense cosmic systems and the development of interconnected filamentary structures known as the Great Web. The presence of these world groupings and the self-organizing web structure unequivocally upholds the hypothesis of the old Big Bang. How systems are dispersed across the universe lines up with the gravitational impacts anticipated from a thick, extending state, as proposed by the hypothesis. These parts, including the grouping of universes, the self-sorting out web structure, and the spreading of universe groups, strongly recommend that the universe came from a very thick state and has been creating for billions of years. Now, we ought to get back to the size of the plan seen by the JWST. These photographs conform to what we assumed we comprehended about the theory of the universe's origin. As shown by the hypothesis, little universes ought to form and extend through impacts and hardenings with different universes. Anyway, the galaxies made by the JWST appear to be altogether different from this thought. Accepting that massive arrangements were connecting and merging, true to form, we would see proof of these impacts and mergers. However, the photos show something different. The Big Bang is still a genuinely wonderful theory, basically an idea without definitive verification. Now, it is truly supported by certain proof, including perceptions of the redshift of light and experiences from far-off worlds, which propose support for the growing universe hypothesis. Studies showing universes developing their distance from each other propose the normal steady development anticipated by the hypothesis. The spread of light components, like hydrogen and helium, seen all through the universe is too predictable with the hypothesis of the universe's origin. Moreover, the huge scope dispersion of cosmic systems, as revealed through cosmic maps, matches the models anticipated by the hypothesis of how things came to be. One of the essential bits of proof for the theory of how things came to be is the disclosure of the cosmic microwave background, CMB. The CMB is faint radiation that fills the whole universe and addresses the extra intensity from the Big Bang. This gigantic radiation, first perceived in 1965, still lines up with the forecasts made by the hypothesis of the universe's origin. The noticed characteristics of the CMB, its consistency and temperature distribution, strongly support the thought that the universe was once in an exceptionally hot and thick state before going through extinction, a central piece of the hypothesis of how things came to be. The discovery of the cosmic microwave background is an indispensable piece of proof that offers us a remarkable insight into the early minutes of the universe. It fills in as a leftover of the fundamental stages following the Big Bang, assisting with examining the degree of the universe's beginning and advancement. The James Webb Space Telescope, JWST, has been quite possibly of the most expected space mission in recent history. Promoted as the replacement to the Hubble Space Telescope, it was launched on December 25, 2021. The JWST is intended to concentrate on the universe in infrared light, which permits it to peer further back in time than ever before. Its groundbreaking capabilities provide exceptional views of the early universe, galaxies, stars, and planets. While JWST's essential mission is to investigate the development of stars and galaxies, it also has the potential to challenge or refine our understanding of well-established scientific theories, including the Big Bang Theory. The theory of the universe's origin, a brief outline. The theory of the universe's origin is the winning explanation for the beginning of the universe. It proposes that the universe started as a limitlessly small, thick point around 13.8 billion years ago. From this peculiarity, space itself extended rapidly in a process called infinite expansion. Over time, matter cooled and amassed together to form the galaxies, stars, and planets we observe today. The theory of the Big Bang is supported by several key observations. 1. Cosmic microwave background radiation, CMBR. This faint glow of radiation is the afterglow of the Big Bang, providing a snapshot of the universe only 380,000 years after its beginning. 2. Redshift of galaxies. The observation that galaxies are moving away from us, with more distant galaxies receding faster, shows that the universe is expanding. This is consistent with the idea of an expanding universe from an initial peculiarity. 3. Overflow of light elements. The Big Bang nucleosynthesis model predicts the relative abundances of elements like hydrogen, helium, and lithium, which match observations in the universe. However, while the theory of the universe's origin has held up for a long time, it doesn't provide a complete picture of the universe's beginnings, nor does it fully explain certain cosmic peculiarities. This is where the James Webb Space Telescope becomes essential. The role of JWST in understanding the early universe. The JWST is designed to address some of the gaps in our understanding of the universe, especially its early stages. Unlike Hubble, which primarily observes ultraviolet and visible light, JWST focuses on infrared frequencies. This is important because, as we look further into space, we are looking back in time. Light from the earliest galaxies has been stretched due to the expansion of the universe, shifting it into the infrared range. Some of JWST's key scientific objectives include 1. Investigating the first galaxies. JWST is able to peer back to within a couple hundred million years of the Big Bang, allowing it to focus on the formation of the first galaxies. This period, known as the cosmic first light, remains largely unexplored. By studying this period, JWST can provide insights into how galaxies, stars, and black holes initially formed. 2. Investigating exoplanet environments. The telescope's infrared capabilities enable it to analyze the atmospheres of exoplanets, including those in the habitable zone of other stars. By examining their composition, JWST could help answer questions about the potential for life beyond Earth. 3. Observing reionization. The universe underwent a phase change known as reionization when the first stars and galaxies emitted ultraviolet light, ionizing hydrogen gas and allowing light to travel freely through space. JWST's observations could refine our understanding of this crucial transition. Potential challenges to the theory of the Big Bang. While JWST's primary mission is to observe the early universe and refine existing cosmological models, its discoveries may challenge some aspects of the Big Bang theory. For instance, JWST might uncover surprising features of the universe that don't align with current models of cosmic evolution. One of the major questions JWST aims to answer is how the first galaxies formed. Current models of galaxy development suggest that the first galaxies should have formed relatively slowly, with their stars being extremely young and low in mass. However, some theoretical models suggest that galaxies could have formed much earlier than expected, with certain models predicting that galaxies could have appeared just a few 100 million years after the Big Bang. If JWST detects fully formed galaxies or structures that challenge the current timeline, it could force researchers to reconsider the processes behind early galaxy formation.